In addition to being fixed, nitrogen can enter ecosystems through deposition. Nitrogen is deposited in ecosystems in particulate, dissolved, and gaseous forms. The rates of deposition vary across ecosystems. At the low end, for example, for ecosystems that are downwind primarily of marine ecosystems, the rate can be as low as 0.1 grams per meter squared per year. At the high end, downwind of agricultural systems with a lot of losses, it can get up to 10 to 20 grams per meter squared per year. That's an extremely high rate. Human activities are now the major source of nitrogen deposited in many areas of the world. This is a map of nitrogen deposition rates at 3 different times. The first is in 1860, before humans discovered how to fix nitrogen. Here, deposition rates tend to be relatively low. The units here are milligrams of nitrogen per meter squared per year. So if you divide by 1,000, you get grams. So by the time you hit orange, you're at 1 gram per meter squared per year. 0.5 is considered a reasonable background rate. And again, the lowest rates that we had were downwind of marine systems, which is 0.1 grams per meter squared per year. So green is considered to be elevated. And you can see that rates were thought of as being pretty low, and there are some systems that might get up to just under 1 gram per meter squared per year. But most of them were in, for terrestrial ecosystems, somewhere on the order of 0.5 gram per meter squared per year. By the early 1990s, deposition rates were being measured a lot more often, and a large chunk of Europe was over 1 gram per meter squared per year, and it was thought to be 2 to 3 grams per meter squared per year in some places too. Most of the rest of the globe, though, was still under 1 gram per meter squared per year. As we forecast into the future for 2050, deposition rates are thought to be increasing and are thought will be a lot higher by then. So 2 up to 5 grams per meter squared per year in many parts of the world. This reflects the increasing use of nitrogen as fertilizer primarily, but there's other sources too, as far as cars are concerned. If you need to think of a breakpoint from when a system really starts to change, 5 grams of nitrogen per meter squared per year is a pretty good breakpoint. Now that critical threshold might be some lower for some systems, maybe 2 to 3 grams per year, and others might be a little bit higher. But ecosystems really start to change at about 5 grams per meter squared per year. And I think earlier we had talked about 4 grams, but 5 grams is about right. The forms of nitrogen also differ for deposition. Nitrogen can be deposited in organic form. It also can come in as ammonium or nitrate. And there's consequences for nitrogen being deposited in each of these different forms. Ammonium, for example, when it enters the system, is going to get nitrified. And that tends to produce protons, which acidify the system. Nitrate, when it enters the system, when it leaves, it tends to bring cations with it. So if nitrate is going to leach out of the system, it tends to bring something positive with it too, which might be potassium, for example, or even calcium. So excess nitrate deposition leads to cation loss in ecosystems. In addition to the chemical form of nitrogen, climate and ecosystem structure determine the processes by which nitrogen is deposited in ecosystems. When we think about deposition, we first tend to think about wet deposition. So you'll have clouds that release rain, and as that rain forms and then travels through the atmosphere, it's going to pick up different forms of nitrogen that are in the air. So for example, NO2 or NO can often dissolve into that water and then be deposited that way, often as nitric acid. So we have wet deposition that brings in often airborne particles or gases that are in the atmosphere and deposits them on a system. We also have dry deposition, and this is deposition primarily of particulate nitrogen onto the surface of an ecosystem. So if there's leaves, for example, you'll get dust that settles onto that leaf, and that dust often will contain nitrogen in one form or another. Lastly, in some ecosystems, you can have cloud water deposition, so fog, and the amount of fog that hits the system is going to depend on the atmospheric characteristics, so whether fog is likely to form, and whether, if you're on a mountain, clouds are likely to form at that altitude. But it also depends on the characteristics of the canopy too. So relatively rough canopies that have a high surface area, such as pine trees, tend to be pretty good at capturing fog, and compared to a deciduous tree would have a lot higher rates of cloud deposition. If we think about the differences among ecosystems in how nitrogen is deposited, whether it's wet, dry, or cloud deposition, this shows patterns among a range of ecosystems in the relative importance of cloud deposition, dry deposition, and wet deposition. These ecosystems are ranged from high to low elevation, and most of these are in the eastern part of the US. When we compare these ecosystems, you can see that really only a few get substantial amount of nitrogen from cloud deposition. Yet, the rest have a balance in dry and wet deposition. If we compare the heights of these bars, they actually tend to be pretty similar, and we think of as wet deposition as being more or less equally as important as dry deposition. Lastly, the authors have a short paragraph on the weathering of sedimentary rocks. In most ecosystems, we think of nitrogen being input from above. And this means nitrogen gas that's fixed, or some kind of dry or wet deposition that happens in an ecosystem. But in some ecosystems, there's actually sedimentary rocks underneath that ecosystem that has marine nitrate. This nitrate is very old. It was entered into the rocks when these rocks were laid down as sediments, and it appears that there's some accessing of this sedimentary nitrate by plants. People are still kind of working through those systems, but the authors wanted to include a paragraph just to let you know that it's possible for plants to get some of their nitrogen requirements from sedimentary rocks. The extent of this we're still trying to figure out, but it's an alternative pathway for increasing the amount of nitrogen in an ecosystem.